Oh well. All right. Two working. So I've got this handout that's going around here. And we're just going to look at the first problem because it's a similar to a homework problem that those of you in Barnes class have to look at, and it's a good problem anyway. Um, and someone asked about it. I will post solutions to the whole handout though, so if you're interested in doing some more practice on the rest of these problems, they're good problems as far as having to like read a question and then interpret kind of how we're actually going to count the things, whether you're using the multiplication principle or using combinations or permutations or other things. So definitely it's good to practice this because it's kind of it takes practice to know or to have an idea about like what method or thing you should try to use to count the number of things you're trying to count. So let's do this first example here. Can can we see? Sorry, the screen here is not working for some reason, so I can't see what's up there without actually looking up there. So apologies. More counting practice. So what do we got here? An automated chemical synthesis of DNA has made it possible to custom order moderate length DNA sequences from commercial suppliers. Assume that a single nucleotide weighs about 5.6 times 10 to the negative 22nd grams. And there are four different types of nucleotides. What are those types of nucleotides? I'm thinking ACTG, right? Like your usual DNA, whatever. I don't really care what they're called, but that context helps me be like, okay, I kind of know what I'm talking about. If you wish to order all possible DNA sequences of a fixed length, at what length will the weight of your order, I add that word, exceed 100 kilograms? All right, so let's just talk about how much it's going to weigh if we order like all of a certain length. So for example, if I wanted the total weight of say let's see, all sequences of length 2, just to kind of think about what's going on here. So how many are there? Well, let's actually write them down. There would be, you could have A then A, or A then T, or A then G, or A then C, or CA, or CC, or CT, or CG, or four more that start with G, or four more that start with T. GA, GG, GC, GT, and TA, TC, TG, TT. All right. So now the real thing I want to write down though is how much will these all weigh? So what is the weight of all of these length 2 sequences? Okay, well, how many of them are there? 16, 4 squared. How many nucleotides do each of them have? 2. So if I wanted to order all DNA sequences of length 2, I would be ordering 16 sequences, each of them having 2 nucleotides. So my total order would have 32 nucleotides. And the weight of that would be 32 times 5.6 times 10 to the negative 22nd. So my answer here would be 4 squared times 2 times the weight here, which is 5.6 times 10 to the negative 22nd. And I don't really care what that is, but I guess I kind of care what that is. So let's use the calculator here real quick. 5.6 times 10 to the negative 22nd. So let's see, we get 16 times 2, which is 32 times 5.6. So we get 32 times 5.6. That's going to be 179.2 times 10 to the negative 22nd. Or if I move that decimal over 2 places, 1.792 times 10 to the negative 20th. I think. Yeah, that's right. Because 179 is 1.79 times 10 squared, and the 10 squared times 10 to the negative 22nd becomes 10 to the negative 20. Clearly not even close to 100 kilograms, right? This is 1.792 times like a very, 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 very small amount of grams. But this is going to help us figure out how we answer this question. So I'll just point out that if I wanted all sequences of length 3, same idea. There, instead of being 4 squared equals 16, which is of them, there'd be 4 to the third of them. There's 64 of them, but now each of them has 3 nucleotides. So that's the number of nucleotides we're going to have, and then they all weigh the same terrible number, whatever. Okay. So the problem here is that we're trying to figure out for what length, I'm going to call it X, is 4 to the X times 5.6 times 10 to the negative 22nd going to be bigger than 100 kilograms. Or I might just change it back to gram. No, I'm going to do this. So this is in grams. Be more than 100 kilograms. And unfortunately, you can't really solve an equation like this, right? If you set 4 to the x times something equal to a number and then try to solve for x using algebra, you can't. So unfortunately here, you just have to kind of guess and check. It's kind of annoying. So here's what I'm going to do to make this a little bit better. I'm going to change this to being measured in kilograms instead of in grams. Meaning, well, if I had 1,000 grams, that's 1 kilogram. Or if I had 10 to the third grams, that's 10 to the 0th kilogram. So essentially I have to decrease my power of 10 by 3. So what I really want is 4 to the x times 5.6 times 10 to the negative 25th. That's in kilograms. And I want that to be larger than 100 kilograms for some value of x. For the smallest value of x, I should really say. Right? You could pick x to be really big and obviously meet that condition. But the question is, at what length will your order exceed 100 kilograms? Meaning we want to find the first length, not the 20th one. So doing this with a calculator is dumb. I'm not doing this with a calculator is not the easiest way to do this. We should use other tools. So I would do this using Desmos. You were working a second ago. Sorry, not you all, but screen here that I wish I could see, but I can't. Let me try one thing here. The easiest thing, unplug it and plug it back in. What was there? Okay. There you go. So, yes. Sorry, let me reshare my screen. So happens when you unplug it and you plug it in again. So here's what I mean. I'm trying to find the value of x so that 4 to the x times 5.6 times, I don't love my choices here. I'll just use another parentheses. And then 10 to the negative 25th. Bless you. So I want that to be bigger than 100. So obviously for early values of x, not very big. Now here's one way you could do this. You could grab a table. Cool, let's grab a table. And let's just start picking some values of x. Let's try 10. Okay, it's not even close to 100. Let's try 100. Oh, too big. Let's go back to I don't know, 50. In the realm of reasonableness, let's try 30. Okay, a little bit bigger. Let's try 35. Getting there. 38. Okay, 39. 40. So it looks like 41 is probably going to do it for my example. Because at 41, we're just over 100 kilograms. Now, if you didn't like this guessing and checking, another way you could have done this is you could have literally drawn the line y equals 100 and then zoomed out a bit. and tried to figure out, okay, they're crossing right. Oh, look, they're crossing right there when x is 40.9. So to be bigger than that, x needs to be 41. Right? If you make x equal to 40, you're not quite there. So lots of ways you can solve a problem like this. Yeah. Because the weight was given in grams and the question was given in kilograms. I could have instead, so another way I could have done this, which is worse for this way of doing it, is I could have left it as 10 to the negative 22nd, but then I'm trying to be larger than not 100 grams, but 100,000 grams, right? Because 100 kilograms is 100,000. So then I have to, then it's harder to zoom out to get to this. Now we still get the right answer, right? X being 41 is still going to give us your 100. Right. Now I'm like, oh, sorry, this changed though. Right. But here, so here 41 gives you slightly more than 100,000 grams, which if I went down to 40, let's just do this instead. Right. 40 is still not quite big enough. It's 27,000 grams or 27 some kilograms. But the reason I didn't do it this way when I was thinking about it is because if you try to zoom out to see where these lines cross each other, you have to zoom like way out, right? Like, and then you can't really see anything at that point. Like I can't see kind of any reasonable value for x there. Yeah, it's oof. Anyway, it's yeah, there's the 48, and then you still right, okay. Somewhere there, sure, that seems totally oh well, you can kind of see it, so but it seemed better to do it the other way. So either way, it's fine. Just make sure the point there is make sure you're comparing like units with like units, right? If you want to know the number you need of things that weigh in grams, then you need to compare to grams or change to kilograms. Any other questions about this one? It's kind of a weird problem, but again, it's just really talking about your ability to count these things and then think about, well, what all of them weigh. And when I did this problem the first time, which was like, I don't know, 5 or 6 years ago, I totally missed, well, because this problem gets assigned like every quarter. It's always a problem, always shows up. I kind of missed the fact that you had to count how many nucleotides were in a nucleotide of length 3. I was like, oh, well, there's 64 of them, but I forgot that they each have a weight of 3 times 5.6 times 10 to the 27. So it's kind of important to pay attention to all the little different pieces here. Okay. Yeah, let's go over this way. So, oh, you're not in the right place. One sec. Apologies. So in my example, my answer was x equal to 41. If you have this question, you probably have a different value for the number of kilograms, and so you might get a slightly different value of x. And then you could also answer this question, but it's really the same idea, right? You're just trying to guess what value of x is going to make the total mass bigger than 5.9736 times 10 to the 24th. It's obviously, excuse me, going to be a much larger number, but still guessable. You just have to keep guessing. All right. In general, when it comes to trying to kind of figure out how to answer a question about counting, there's no good rules to follow. It's kind of like you got to practice it until you can kind of make sense of what's going on. The only things I really kind of think about when I'm looking at a problem like this is, do I care about the order of things or not? That's usually meaning has some sort of permutation versus combination aspect to it. And what's the other thing I was thinking of just a minute ago? Oh, and if we're using the word and, we often multiply. If we're using the word or, we often add. But really, like, there's not really great rules for probability. It's a definitely you have to play with it to figure it out kind of process. Again, I will post the solutions of the rest of this. I'm happy to, I mean, not that you should look at it right now, but if you have questions about it later, also happy to talk about it, but the solutions will get posted on Canvas later today. All right, where were we last time? We were talking about conditional probability last time. Look at my notes here. Go notes. Yeah, okay. Let's go this way. So just a reminder, conditional probability. This is 5. Oh, not 5. 6. We're in June. /2 /25. Co-17C. So more on conditional probability. So I'll just say it. When I think of, well, that's fine. That's fine. Sorry, but maybe it's slightly better to see. Whenever I hear conditional probability, the first thing I think of is this formula. The probability of B given A is the probability of A and B divided by the probability of A. That is the formula that sticks in my head. That's the one I would encourage you to remember because I think it makes the most sense. You're saying I'm already stuck in A, and then I want to know what's the chance of being in B, which means I also have to be in A since I'm already in A, given that we're in A. And then last time we also talked about the fact that A and B are said to be independent if the probability of B given A is equal to the probability of B. Or similarly, the probability of A given B is equal to the probability of A. Or less similarly, but still true, the probability of A intersect B is equal to the probability of A times the probability of B. These are the three kind of ways you can test to see if two events are independent. And all these first two ones say is really that the first one says the probability of B is unaffected by knowing whether or not A has happened. Probability of B in general is the same as knowing A has happened, the probability of B is still the same. So knowing A has happened doesn't change the probability of B happening. I want to make a clear distinction here. This is definitely very different than two events being mutually exclusive or disjoint. Being mutually exclusive means if one happens, the other one cannot happen. So just to kind of remind you, on the other hand, A and B are mutually exclusive or disjoint if there's no overlap. We can either write it as A intersect B is equal to the empty set, a set containing nothing, bless you. Or some people write it as the Greek letter phi or phi, the zero with the slash through it. Or you can write it as the probability of A intersect B is zero. Whereas here, for events to be independent, there's got to be some overlap. Well, I mean, there should be some overlap because, well, here's another way to think about it. If two things are independent, let's say, I always have, sorry, not even mutual. I always have a hard time. Okay, here's a good one. Every integer number is either even or odd. So if you know a number is even, do you know anything about whether it's odd? If I tell you that the number I picked is even, what can you tell me about its oddness? Is it odd? No, but you know it's not odd, right? So if I tell you a number is even, what's the probability of it being odd? Zero, right? These events are not independent because knowing one has happened affects the probability of the other one happening. So if two events are disjoint or mutually exclusive, like being an even number or an odd number, they cannot be independent of each other because knowing whether or not one has happened fully informs you about whether or not the other one has happened. And that's the total opposite of being independent. And then I always like to say, being independent and mutually exclusive are mutually exclusive. You can be one and not the other, but you cannot be both. Except for one really stupid exception that people try to make an example of, which is dumb. It's not a good example. So you can't be the same unless people let you dumb about it. Sorry, there's one problem in the book somewhere. I was like, this is a terrible problem. You should not use this. All right, so sorry, let's actually do some real examples instead of just me saying things. Where'd you go there? Sorry, I got a little off there. We were there last time. Cool. So we did that one. Okay. So why don't you all try the following? We'll do this one together first, actually. So example, find the probability. We're drawing cards from a deck of drawing. Yeah, that's not the word I want to use. Of the card that you have drawn being a king, given that I've told you it's a club. Right, you drew a card, I looked at it and said, it's a club. And then now I'm asking you, what's the likelihood of it being a king? So let's label our events. Let's say that event A is being a king. I will point out we're probably doing more work than we really need to here. You could just kind of write like you could write that I want to find the probability of being a king given it's a club if you really just want to kind of go that way. But I'm going to be a little bit more process oriented here. And event B is being a club. I'm going to again emphasize here there's two ways you can approach these conditional probability questions. One way is to look at your reduced sample space. Also, actually, before I go this way, before we talk about reduced sample space, we're trying to find the probability of something given something else. I want you all to write down if it's A given B or B given A. Again, the one that you know has happened should be the second thing you write down. Let's do before. All right, I told you it's a club. So being a club is the given piece of information. So the B should go there, the A should go there. We're trying to find the probability of A given B or getting a king given that it's a club. All right, so given that our card's a club, our reduced sample space, our omega B is the set of clubs. It's the ace of clubs, the two of clubs, the three of clubs, all the way to the 10 of clubs, jack of clubs, queen of clubs, king of clubs. I can't draw a club. So these are all clubs. Okay, so given that those, like I took all the other cards out of the deck, and given that these are, how many cards are these? Given that we only have these 13 cards, the probability of getting a king is, well, 1 out of the 13 cards. So the probability of A given B here is going to be 1 out of 13. One way of getting what you want out of 13 ways of anything happening. Or we could go the formulaic way. We can say, well, the probability of A given B, we use the usual formula. It's the probability of A and B divided by the probability of B. Now, when you do it this way, you have to remember that you're working with the entire sample space, the entire deck of cards. So I usually like to look at the bottom part first. Probability of B, which is being a club. All right, what's the probability of being a club? Right, 13 out of 52, which you could, although you really don't want to, reduce to 1/4. And then A and B, that's being a king and being a club. Well, there's one king of clubs. So there's a 1 out of 52 chance that your card is both a king and a club. And then obviously the 52s cancel here, and we also get 1 out of 13. I will point out as well, these two events are independent because A and B are independent. Independent is a word I can spell because we know that the probability of A itself, the probability of being a king is 4 out of 52, which is 1 out of 13, which is the same as the conditional probability we just calculated. Just to go one step further with that, I'll also point out that you could calculate it. I never like doing it this way, but you could also say the probability of A times the probability of B. Well, we just said the probability of A is 1 out of 13. Probability of B, the probability of being a club, we said was 13 out of 52 or 1 out of 4. And that is equal to 1 out of 52, which is the probability of A intersect B, the probability of being a king and a club. So that's another, so this also shows that they are independent. I don't know how much your teacher cares about independence. It's just something I know is important in stats. So that's why I'm kind of like, well, this seems like an important topic, but maybe I'm hammering on it too hard here. Let's look at some other examples. Definitely want to get to, let's look at some other examples quickly. Also, right, some, not tomorrow. Wednesday is our last class, right? There's no class on Friday, right? People have finals on Friday. Let's do this next example. A family has two children. This problem might feel annoying in some ways. One of their children is a girl. We'll call that event A. Find the probability that the other child is a girl. That, or as I'm going to phrase, that both children are girls. We're going to call that event B. And you're probably all going to be disappointed to hear that the probability is not 1/2. It seems anti-intuitive. Like, well, if one of the kids is a girl, shouldn't there be a 50% chance the other one's a girl? No. It's kind of weird though. So sometimes probability feels very intuitive, and sometimes it really doesn't. Here's why it's not. Well, let's look at all the things that can happen. So if event A is that one of the children is a girl, well, how many ways can that happen? You could have a girl then a boy, or a boy then a girl, or a girl then a girl. So in our reduced sample space where we know at least one of the children is a girl, there's 3 different possible outcomes. The only one that we can't have is boy, boy. So from our reduced sample space here, right, this is our omega B, our omega A, apologies, right? We know we are given, right, this is the given information. So if we're trying to find the probability of B given A, well, there's only one way of getting what we want out of the 3 ways the thing that we're told can happen can happen. Or, of course, you can use the formula. You can say probability of B given A is the probability of B intersect A divided by the probability of A. And the probability of getting B intersect A where at least one is a girl and both are girls is really just the probability that both children are girls. And there's a 1 in 4 chance of that happening because not written down here is boy, boy. So there's your probability of B intersect A. And the probability of A, the probability that at least one of your children is a girl, is 3 out of 4, which is 1/3. So I think the way this question is written in a confusing way on purpose. If the problem had been worded instead as we're told that at least one of these children is a girl, it's more obvious that, oh, where the girl is in the birth order kind of matters, right? We're not told that. So there's really 3 different ways you can have at least one girl. Girl first, then boy second, boy first, then girl second, or girl first, then girl second. Question, yes.
But if the order matters.
Practice, experience. There's not a good, right, there's not a good like way to know. I'm sorry for this because it's true. Like it really is just like a practice doing problems like that. Okay, well, in this case, it seems to make sense. Whereas if I'd written this problem in just a slightly different way, another family has 2 children, and now we're told the oldest child is a girl. What's the probability that both are girls? Well, now our reduced sample space is smaller, right? You could either have boy, girl, or girl, girl. girl, boy is not an well, sorry, I'm reading this like the second one is I've kind of written this in the backwards way, maybe. Let me rephrase here. We could have girl, girl, or girl, boy. I was thinking of the second one being the oldest, but that doesn't really make sense if you think about it. So here's our that's event A, that's event B. Here's our reduced sample space. And the probability of B given A that the oldest child is a girl, well, there's only one out of those two ways that the youngest is also a girl, or that both are girls. So yeah, it's really kind of thinking about like all the ways you can get what you want and all the ways you can't get what you want. There's kind of a very famous probability problem called the Monty Hall problem, where it used to be like people would be given three doors to pick a prize from, and one of them would have the prize and the two wouldn't. So people would pick the door, and then they would eliminate one of the other doors, and it was always better to switch because people thought they had a 50-50 chance of getting it right, being told one was wrong. But that's not true because if you pick one of the doors, what's the probability you picked the right thing if there's three doors? One out of three. What's the probability you didn't pick the right thing? Two out of three. So one of those other two doors, there's a 2 out of 3 chance that one of those is the right one. And then they've told you one of them isn't. So the other one is a better bet, right? You always, if you're playing the Monty Hall problem, whatever, as it's called, let's make a deal or whatever, you should always switch doors because you always have a better chance of not picking the door on the first pick than having picked the right door on the first pick. But people were fooled, right? They felt like it was 50-50. So just to show like sometimes thinking about the probability of something can make a difference. Let's see, what else do we want to say here? Yeah, let's get to the real stuff here. We got time. Cool. Independent, sure. Oh, we should do this one too. Right. One more, and then we'll talk about the next thing. So here's a question that people like to ask. A multiple choice test, which hopefully you will not have in a math class, has 10 questions, each with 5 possible answers. A, B, C, and D. What is the probability of answering all 10 questions correctly by guessing? Right, we're assuming we didn't study for this test, which I know none of you would ever do. All right, so what's the probability of getting all 10 correct? Or another way you could write this, people often do this where they say, we're going to let X equal the number of correct answers. And then we're going to say, what's the probability of getting X equal to 10? Well, what's the probability of getting the first question right? 1 out of 10 or 1 out of 5? 1 out of 5. What's the probability of getting the second one right? Does it matter what we did on the first one? Is each test question independent? Yes, they are, right? The probability of getting the first one right doesn't affect the probability of getting the second right if you're guessing. So it's going to be 1/5 times 1/5 times 1/5, 10 times, or more easily written as 1/5 to the 10th power, which is super duper small. It's like 1.024 times 10 to the -7th. So not very good odds of getting all 10 questions right if you're just guessing. Here's a more interesting question. Probability of X being bigger than or equal to 9. So that's going to be the probability that X is equal to 9 plus the probability that X is equal to 10. We already know what this is. That's going to be 1/5 to the 10th. The probability that X is equal to 9 is a little bit more interesting of a question because we have to think about two different things here. First of all, what's the probability of getting exactly 9 questions right? Well, let's say we got the first one wrong. What's the probability of getting the first one wrong? And you want to say it. 4 out of 5, exactly. 1 minus 1/5. So the P, people call these like P and Q often. P is your probability of success, Q is your probability of failure, and they always add up to 1. So here, the probability of getting 9 right, where the first one is the one we got wrong, is going to be 4/5 times how many 1/5? 9 of them, so 1/5 to the ninth. However, I made an assumption that not isn't necessarily true. I said we got the first one wrong, but we didn't have to get the first one wrong. We could have gotten the second one wrong, or the third one, or the fourth one, or the fifth one. How many different ways can we get one of them wrong? 10 ways, or as I would say, 10 choose one. Or what we should actually write is how many ways can we get 9 of them right? 10 choose 9, which is also still 10. And that's the formula for the probability of getting 9 of them correct. It's 10 choose 9. You're going to choose, how many ways you can get the 9 of them correct, multiplied by the probability of getting one of them wrong and 9 of them correct. And then if you want to go one step further, if you want to find the probability of getting, say, exactly 8 of them correct, it's the same deal. You're going to do 10 choose 8 times 4/5 squared times 1/5 to the 8th. 8 right, 2 wrong. How many ways you can get 8 right? All right, so let's go ahead and look at the next thing, which is the build up to Bayes' formula here, which I think we have enough time to get to at least the end of this first example here. I have to imagine that Varn will give you a question almost exactly like the one we're eventually going to get to. I don't know as much about Lee, although almost always this type of question gets asked. So here's all the words, which is kind of a lot of them. A blood test for a disease shows a positive result in 98% of the cases when the disease is present. And in 6% of the cases when the disease is not present. Called a false positive. Right, you're getting a positive result and you don't have the disease, it's a false positive. And then we're going to assume the prevalence of the disease is 1 out of 250 people. Or if you prefer, 0.4%. Before we get going, let's actually write down what we know. So I typically like to say, sure. I usually say that like, I'll use the notation here. So let's say A is having the disease. B is getting a positive test. And then I don't think we've talked about this notation yet. A complement, people use a C or sometimes they use like a prime, although I think a C is more typical notation here. A complement is everything that's not having the disease, so they don't have the disease. Something that's true about a set and its complement, or an event and its complement, is you have to fall into one of the two categories, right? If there's this disease in the world, either you have it or you don't. There's no other choice. So you're either in A or A complement, and the two things that are true about a set and its complement is their overlap is empty. I could also say they're disjoint or they're mutually exclusive, and their union is everything. A union A complement comprises every single person in the world. Every person either has this disease or doesn't. So just something to be aware of. We're talking about complements. The intersection of A and A complement is the empty set. There is no overlap. The union of A and A complement is everything. It's your entire, oh my gosh, what's the word? I can't remember the word. What's your entire, is it sample space? Yeah, it's like it's your entire, okay, that's what I thought it was, but yeah, I was losing it there. It's your entire sample space, omega. So B complement is having a negative test. Right? If you take this test, you either test positive or test negative. There is no other, we're assuming this test is always positive, right? It's not like, well, we're inconclusive, no, none of that stuff. So here are the things we know so far. A blood test for a disease shows a positive result in 98% of the cases when the disease is present. That is a conditional probability statement. They have told us it is given that the person has the disease, and we're being told the probability of testing positive is 98%. So the probability of B given A, probability of testing positive given that they have the disease is 0.98. They also tell us that the probability of testing positive when the disease is not present is 6%. So the probability of testing positive, still B, given that the disease is not present, is 0.06 or 6%. There's also other probabilities we could write down, but I find it hard to think of them when I'm writing things like this. So what I would say is a better way to write things down like this is using what we call a tree. So for any kind of problem like this, where they're giving you like positive, negative testing here, I think it's always good to use a tree. And typically, the first branch of your tree should be having the disease or not. So you can either have the disease or not have the disease. And what's the probability of having the disease? Well, what's the prevalence of having the disease? I think it was 1 out of 250. So the probability of A is 1 out of 250, which means we also know the probability of not having the disease. It's all the leftovers. It's 1 minus the probability of A. So the probability of A complement is 1 minus the probability of A, which is 1 minus 1 over 250, or 249 over 250. So the probability of A complement is 249 out of 250. Something that's nice about these tree diagrams, which this is not, you cannot see that very well. One thing that's nice about these tree diagrams is that every branching, the branches should always add up to 1 or 100%. Because one of those two things has to happen. And if you sum all the probabilities together of all possibilities, they always have to add up to 1 or 100%. Okay, but now we have another branch. And in this branch, you can either test positive or test negative. Now, I really don't just want to write probability of B here, because it's not just the probability that B happens. It's the probability that B happens given that A has already happened, because I'm on the branch where A has already happened. And that probability is going to equal, well, they told us it was 0.98, which means we also know the probability of testing negative given that you have the disease. You either test positive or test negative if you have the disease. If there's a 98% chance of testing positive, there's a what percent chance of testing negative? That one more time? Yes, or I would say 2% or 0.02. Yeah. Right. We're just subtracting from 1. Same deal down here. If we know that the probability of getting a false negative, so testing positive given that you do not have the disease, is 0.06, then the probability of getting a true negative, or whatever you call it when you accurately test negative, that's going to be 0.94. Plus, you might feel like this is more work than we need, but it's really not. So we'll see that when we ask this question. Question A, if a random person is given the test, so we don't know if they have the disease or not, which is usually why you would take a test to see if you have it, right? You're not taking the test because well, I mean, often you are like, I think I have the disease, but you don't actually know. If you already knew, you wouldn't take the test. You'd be like, I have it or I don't. What is the probability they test positive? Okay, this is where things get easy if we use the tree. So when I find the probability of testing positive, it's just all the pathways that get me to a positive result. So there's one pathway here, right? B is a positive test, and there's another pathway here. So my probability is going to equal the probability of testing positive, which is the probability of B. It's going to be all the ways I can test positive. It's now watch me write this down. Here, okay. Here's what I really write down. I would say it's 1 over 250 times 0.98 plus 249 over 250 times 0.06. But it's also nice to talk about where this formula is coming from. So what we're really doing here is we're saying this is the probability of A intersect B plus the probability of A complement intersect B, which is also known as the law of total probability. We're trying to find the probability of B happening. It's all the ways B can happen with intersected with any of the other events that can happen. So either B and A can happen, right? You can test positive and have the disease, or you can test positive and not have the disease. And those are the only options. And then we know the probability of the intersection is the probability of A multiplied by the probability of B given A. By the way, I want to point out right here, it's not probability of A times probability of B, it's B given A because this is a conditional probability, and we know that the events are not independent. Right? If they were independent, it'd be probability of A times probability of B. So I don't usually get that though. Similar deal here. It's the probability of A complement multiplied by the probability of B given A complement, which is exactly what we wrote out up here. Right, so I'm kind of zoomed in here, but that's exactly what this is. It's the probability of A multiplied by the probability of B given A complement plus the probability of A complement times the probability of B given A complement. But the tree makes it so much easier. Just like find all the paths that get us to B. Now, here's what I want to point out. As you travel along a path, you have to use an and. We're going to have this happen and this happen. So we multiply them together. Or add this route can happen. Probability of A complement and probability of B given A complement. So that's why it's this times this plus this times that. Because it's this route or this route. Okay. Also, this ends up being approximately, what did we get here? 0.0638. We're almost out of time. So let me say one more thing here, even though we're almost out of time. So the question people really want to answer here is, what's the probability of having the disease given that we tested positive? In other words, what's the probability of A given B? Now I want to make sure it's really, really clear. This is not the same as the probability of B given A. Right? This here is testing positive given we have the disease, which is like 0.98. And yes, you're welcome to go if you need to go, but I do want you to just see this last part here because it is kind of cool. You don't have to say, but if you can say, you should say. So the probability of A given B is the probability of A intersect B divided by the probability of B. Now, I'm really just going to use my tree again. So look, A intersect B, well, that means A and B have to happen. So it's going to be A and B. So this times this. So it's going to be the probability of A multiplied by the probability of B given A. And on the bottom, we already did that. And that was the last question. Probability of B is just, again, all the ways you can get to B. So I keep kind of going off track here. All the ways you can get to B are either going to be, well, the one we just calculated, probability of A times probability of, whoops, a little bit messy there, B given A, plus the probability of A complement times the probability of B given A complement. I've probably never actually memorized this formula in my whole life. I've probably actually drawn this tree every time because it's just more convenient. This is base formula. This is how you get the reverse conditional probability based on having the other conditional probability. This ends up equaling, I have it, I don't think I actually have it in my notes here. So it's 1 over 250 times 0.98 divided by the same 1 over 250 times 0.98 plus 249 over 250 times 0.06. Now, I do want to calculate this for you just because I do think it's worth knowing what the number is. So 1 sec, and then you're free to go. So 0.98 divided by 250. 392, sorry, 1 second. And then we have plus 249 divided by 256. Right, cool. And then 0.00392 divided by that answer. We get, I don't love that. Oh, no, I do love that. Sorry, 0.06155. So I want to be super explicit here. The probability of testing positive, given that you have the disease, 98%. The probability of having the disease, given that you tested positive, about 6%. Right? Very, very different. And it's more based on how prevalent the disease is than how good your test is. It doesn't matter that your test is testing very, very well. It's not going to tell you that someone has the disease because the disease is very, very unlikely to be spread throughout the population. So don't confuse the two, right? Having the disease, given that you tested positive, is very, very, very different than testing positive, given that you have the disease. But it's easy to conflate them. So make sure when you're doing these problems, read the words carefully. It's all about reading comprehension here. All right, I'll see you on Wednesday. And I'll be over and drop in from 1 to 4. You get out of here because I assume that next class is itching to get in here. I don't have I have the one I wrote on, but it had like exactly enough copy. Oh, is there no. I'm happy to print one out for you, but I don't have one on. You're welcome.
Just for this one, I know we were doing it, the probability, so we just have to be careful because although they look similar, they're gonna be different.
Now they can come out to be similar,
Okay.
but there's no reason they have to come out to be similar.
Okay, got it. Thank you.
You're welcome.
So
Yes.
I know that I need to come here like 20 times in order to pass,
Yes.
but I was planning on coming because right now I'm 19
Okay.
and I was planning on coming Friday, but it's like Friday.
Oh, that's not Friday.
Yeah, because like Wednesday I have like an appointment on the embassy because I have to
Sure.
my passport and stuff. So
Let me take a look.
okay.
But obviously you should go to your passport.
Yeah.
You should go to that.
I mean, I've been watching the recordings. That's why I asked about if like there were going to be like any makeups.
Right. Unfortunately, I don't really do makeups, but again, I'll take a look and I don't think it'll difficult.
Okay, thank you.
Yeah.
The gradient dotted with the unit vector in the direction that you're taking the derivative in.